Hello and welcome back to differential equations. Now we are going to talk about 5.4, which is another applied section for us to deal with in area of mechanical engineering. This time we will be talking more about spring mass systems, and hopefully you remember what the equations looked like when we had only one of those systems. So now we are going to have multiple. We're going to have a system of multiple equations. So what we know from one system, right? If you have, maybe I should label this as old. If I label this as old, I will say we had something like this. There's a spring with a constant K, there's a mass M, and the dashpot there, which gave us a C. And we had the distance x that we worried about. So we had mx double prime plus cx prime plus kx equals to some forcing term f of t. So that's what was old. And we solved that using variational parameters, undetermined coefficients, right? We used the formula with R, if you remember, right, to come up with the solution. So that was it. Now, what are we doing now? Now we're going to have multiple objects connected with multiple springs, and they are going to oscillate, and we're not going to use any dashpots here. We're not going to have any of the forcing. We're going to take a look at the simplest possible case, which has only masses and springs. Now, obviously, once you learn well the simplest case, you can go ahead and upgrade to harder cases, right, with adding more either more masses and more springs, or introducing dashpots and external forcing and so on. So now the new is going to be multiple masses. You can have as many of these as you want, and they will be connected with the springs that are going to have different Ks, right? Because you can determine the stiffness, right? K determines the stiffness of the spring. That's a spring constant in newtons per meter. And that will determine the motion, the x1 motion, the x2 motion, and the x3 motion happening over here. So if you have three masses, you are getting three equations. So we have, so each one of these x1s, that's how far the spring is stretched. So this spring stretch is just x1, right? But this spring here, stretch is given as x2 minus x1 in distance, because this is the stretch of the second spring. But remember, when that's stretched, and if this x1 pulls the other way, at that time, because the springs are always trying to do the opposite of what we actually, they always have the opposite reaction to what you do to the spring, right? If you compress it, it wants to expand. If you expand it, it wants to compress. So all of these, right, would be stretches that are subtractions, right? And the last one is just having the x3 stretch right here. So I hope that makes sense. And these are simple linear lengths. There is nothing special, right? Because if these springs are all attached and you stretch 1 inch, the other one has to compress 1 inch in order for, right, them to still be attached to each other. So whatever is a gain of one, it's a loss of others. Whatever is a loss for one, it's a gain for other, and so on in terms of the length. So I hope that these equations here make sense. Now, since we are not going to have our mesh, I'm going to have masses and then distances plus kn xn equals to, and we are in this case working with 0. So if I am to use this equation to set up the situation for all of the masses, right, for each one of these motions, I would have m1 x1 double prime, which is we have to set up for all three masses, right? And as you can see, all three masses have springs attached from both sides, right? So this one, and then plus stuff with k equal to 0. We don't have a c term because we don't have the dash pot. So this is where the k stuff goes. Now, what is the k stuff? Well, we definitely have, if we had nothing else, right? If you're really trying to learn how to model these things, because, I mean, this is your life if you're a mechanical engineer, right? You throw this away, and you're just looking at the K1, right? Well, the K1 part is going to be just a K1x from, your previous K1x1, right? That's from your previous life. There's nothing there, right? But then this is bothered by the K2 from the other side, and the K2 has this stretch of a distance for x, right, associated so that's going to be minus K2, and then minus K2, and then we have x2 minus x1. There we go. So that's our first equation looking at the springs. Let's take a look at now mass 2. So mass 2 times x2 double prime, and then again plus and some k's go in here. So what are the k's? Well, I have a k on the left and I have a k on the right. So there's the k2 and k3 are spring with a spring constant k2, and the spring with a spring constant k3 are the two springs that are connected to the mass 2. So I will have my k2, and then k2 is x2 minus x1 for distance. And then I am going to have minus k3 of k3 is x3 minus x2 equals to 0. So let me just check that. Okay. mass 3x3 double prime plus, again, no x prime term because we have no dash pot. We could have put, instead of k4, we could have put dash pot there, right? So that equation would have a c in it. We didn't. So, right. Now, this is, again, k's go here. So k3 and k4 would go in there. What do I have? I have k3, which is x3 minus x2. Again, that's the displacement for this one. And minus k4 x3. Oh, the distance for that one. Okay, so when this one stretches, this one compresses. There is, but this is fixed over on the other side. So we don't have the difference. The difference is 0 minus x3. It's 0 minus x3, so this is a plus. That's a plus because this is supposed to be 0 minus x3 if you want a minus there for the distance. I hope you see the pattern. It's x1 and then x2 minus x1, then x3 minus x2. This should be x4 minus x3, but there is no x4, so that's a big fat 0, and it becomes negative x3, and that changes this sign to a positive. I don't know if that makes sense with you guys. I hope it does, but you know, in the modeling you have to be careful with those kind of things. So I guess just replay replay the video so it clicks. I don't know. It's rudimentary physics, but still, you know, not all of you took it, so you might not be okay with modeling there. And we are almost there. We're almost there because I can use now I can solve for these and create my 3x3 system, right? Because I'm going to do this, and then I'm going to say m1 x1 double prime is going to be negative k1 x1 plus k2 x2 minus x1. Now we can swap those, right, to make that negative as well, but whatever. M2 x2 double prime is negative k2 x2 minus x1 plus k3 x3 minus x2. And m3 x3 double prime is negative k3 x3 minus x2 minus k4 x3. Okay, so those are our equations. And now let's make them into vectors and matrices. So to put all of this into a single system, we are going to have to distribute and collect x1s and x2s and x3s, which would create a matrix. And then we also have the M matrix here for masses. So let's take care of the easy ones first. I mean, they're all easy, it's just that it's mess. Well, let's actually distribute first and then we'll deal with this. So mass 1 x1 double prime is equal to, now we have negative k1 x1 plus k2 x2 minus k2 x1. See, this term and this term are like terms because they both have x1. So it will be negative k1 minus k2 would be a coefficient for that. Now we have mass 2x2 double prime is equal to negative k2 positive negative k2x2 positive k2x1 positive k3x3 negative k3x2. By the way, all this mess is just 4 springs. Keep that in mind as we go. And M3, it was always fascinating to me that such a simple system can have such a mess of calculation, right? And then someone asked me, do I have to simplify my answer? Yeah. Of course you do. All right. Just plugged in my computer. Is it charging? Hopefully it's charging. Okay, plugged in. So, negative k3 x3 plus k3 x2 minus k4 x3. All right, now collect like terms. M1 x1 double prime is equal to what? Well, we have a negative k1 minus k2 times x1 plus k2 x2. That's our first equation. The M2 x2 double prime is, what are my x1s? I only have k2 x1. Then I have for x2s, I have 2 of them. So that's going to be negative k2 minus k3 x2. Those would be this term and this term. This term is x1, that's done. And I'm left with plus k3x3. So we're trying to make like x1, x2, and x3 realms, right? So we can write the matrix easily. M3 x3 double prime is, do we have k1? We don't have, x1. We don't have x1. We do have x2. So that's k3x2 plus, and for this last one we have k4, so minus k3 minus k4 x3. Cool. Got them all. And now that I have the system, we can come up with the matrices. So I'm going to start with defining this vector of derivatives, right? So this is going to be my vector x double prime, which is going to have x1 double prime, x2 double prime, x3 double prime. And now, because that's a vector and needs to be multiplied by these m's, but you remember you need to multiply a row into a column, right? We actually have to make coefficients m, which are the masses, times the identity matrix, which is 3 by 3 square matrix. So we have to make capital M times x double prime, and capital M is going to be the matrix of the masses. So now when I have this, on the other side, I'm going to have, k times vector x. Now vector x is just a vector of x1, x2, x3. These are the three unknown functions. Remember, you're solving differential equation. Your job is to find x1 of t, x2 of 3, x3 of t, right? You can call them x, y, z, whatever, u, v, w. I don't care what you call them, but that is the object of this problem. By the way, k's are given to you, right? K's are numbers. You know, K1 is 3 or 100, and K2 is 1,000 or 6, right? It's just gonna, K's are some numbers, so the whole matrix for K collapses down to a simple 3 by 3 matrix, which looks terrible, but it's simple, right? You have your negative K1 minus K2, then you have K2, and you have a 0. Then you go to the next row. You have K2 for the first one, negative K2 minus K3 for the second one, and just K3 for the last one. And then a 0 over here, and a K3 over here, and negative K3 minus K4. These spring constants are given to you because we know how stiff those springs are. We picked them out, right? So, what do we know? We know all m's, those are the masses of objects, you just measure them. And we know all k's, because we know which springs we picked. So the only unknown variables, which in this case are functions, are x1, x2, and xt of as a function of time. This creates a matrix differential equation here, like this. So you know, and as you can see, it doesn't show. We know dimension is 3, right? But it's a very compact way of writing our spring system. And if you had 15 springs, it's still, right, the same thing, except you're just going to have, right, 15 springs is 14 equations. So we need to convert this, right? So this is our application. However, we need to get to x double prime equals a x, right? And in order for us to get there, I need to get rid of m, matrix m. And to get rid of the matrix m, we have to use the inverse matrix to pre-multiply by inverse matrix to eliminate m, because so find m inverse and pre-multiply both sides. I did tell you before, I hate that word, but it's necessary because you have to put before these. The matrix multiplication is not commutative, so it's important whether you put it in both terms before or both terms after, and so on. You can't mix and match. So we're going to get m inverse times m x double prime is equal to m inverse times k times x. This is 1, which gives us just x double prime, and over here we're going to define this as a matrix A, which is the focus of what we are doing here. So this is now what we need to find, and the matrix, right? The matrix here, you can actually use the calculator to get the inverse of the matrix. Inverse of matrix, and it's covered in couple of sections in linear algebra. These things are not trivial to find. Luckily, your calculator has the button for it, so you can find. Now you are supposed to memorize the way to find the 2x2 matrix, because that's what I plug in on the test, so you're not solving these problems for 7 years. So 2x2 case. But I have no doubts that my MATLAB will ask you for a 5x5, just because, yeah, they can. So use the feature in your calculator to figure out the inverse, as long as you know the concept on that you need to pre-multiply by the inverse to get x double prime by itself, right? The rest is smooth sailing. And then from that point on, standard stuff. You're going to have your system, and you are going to solve it by getting the what do you call it? Substitute. Use a substitution to make it a first order system. You solve that one, and then you just integrate one more time to integrate the substitution, and you will get your solution. Now, generally, these solutions are supposed to be the waves, right? They need to be. You need to get complex eigenvalues if you are using eigenvalue method, so that you can come up with a system that has sines and cosines that is oscillating. Now that is when you have forcing. If you don't have forcing, the systems will still oscillate, but then the dashpot would make them stop, which would include e to the negative something and so on. So there's just a lot of mess with these. These problems can be fairly complicated in terms of the solutions. Let's take a look at some of the stuff. Okay, so I should go for the and derive everything, but maybe I can just write solution and of the form, because we're going to do a 2D example rather than the 3D forever. Solution of the form x bar of t is equal to summation of ai cosine omega I t plus bi sine omega I t times vi vectors, and then I goes from 1 to n. What is the n for? It's the number of dimensions. So if you have 3x3 case, you will have 3 terms to add. This is not an infinite series from Calc 2. This is a finite series. And those of you that have seen Fourier series before, this is not a Fourier series either, because it's a finite. You need infinity there to be a Fourier series. So this is just adding 3 terms. Instead of me doing all of this, writing it 3 times with I being 1 and then 2 and then 3 for 3x3 system, I'm just going to put this for any dimension n, right? So any number of unknown functions xn. So that's the solution. Now it will all go back into obviously eigenvalues, eigenvectors, and so on. So let's take a look at the simplest possible case you can have, which is when you just have two masses and two springs. You can make it a little bit more interesting by adding a spring on the other side. So now we have a spring going into a mass and another spring going into a mass 2, and it's not attached to anything on the right. So they're going to have K1 and K2, which are known to us, mass 1 and mass 2, which are known to us, and we are going to have the two displacements, right? We're going to have our displacement x1, we're going to have our displacement x2, and if you remember, this spring over here was x2 minus x1 for the displacement. We don't have another one. If we had another spring here, then that one would be just negative x2, if you remember from the previous, but we don't have it, so that's life, right? So what are the values that are given to us? This is very systematic. Just, sit down and step by step figure out first the modeling, then figure out where they plug into equation. You should already know the way to solve this because that was in our previous lecture, or previous two lectures, and that's it. All right, so what do I have? I have that, mass 1 is 2, mass 2 is 1, K1 is 100, K2 is 50. So I hope you remember, right? Remember that stuff. So now, to create this system, we start with our M1 X1 plus, double prime, plus K1 X1 minus K2 X2 minus X1 equal to 0. Again, we're not bothering the system with any external forcing f of t, so it's just equal to 0. So I have two springs. See, first mass has two springs attached to it. The next equation for M2, X2 double prime, will only have one spring attached to it, and that's K2. And it doesn't have anything else. So hopefully you can visually connect that my mass has two springs attached, and then they are 1, 2, right? Each K represents a spring. The second, you can think of this as a free body diagram and how many forces are acting upon it, right? Oh, by the way, I failed to mention since the beginning, it's frictionless. The whole thing here is frictionless. So all of the forces that we are dealing with, there is the, pack ties from Minecraft. No friction on the bottom. Because if you have a friction, then you are introducing another force. And you have to take that into consideration as well, right? Because the normal force, right, because of the weight of the mass times gravity is a weight, and that's the force that pushes down to the surface, and then the normal force would be opposite force, so it doesn't, break through the floor, right? The floor is strong enough to hold it. creates a normal force which is perpendicular, and then perpendicular force times the coefficient of friction creates a friction in the opposite direction. So there will be another term of for friction if this is added a friction. So you can add dashpot, you can add friction, you can add forcing, and these equations can become a living nightmare to solve, which is why we have numerical methods and computers, right? All right, cool. So that's enough talk. Let's deal with this. I'm going to plug the numbers in so that I can just go through this. So 2x double prime 1 plus 100x1 minus what do I have? K2 is 50, x2 minus x1 equal to 0, and then M2 is 1, x2 double prime plus K2 is 50 of x2 minus x1 equal to 0. So this is our situation with equations. Then I'm going to take a look at I have to distribute everything and deal with that. So I'm going to go with 2x double prime 1 plus 100x1 minus 50x2 plus 50x1 equal to 0, and x2 double prime plus 50x2 minus 50x1 equal to 0. I need those matrices, so I have to do all of this mess. Now, what do? 2x1 double prime, and for x1 I have plus 150x1 minus 50x2 equals to 0, and for the x2 double prime I just have minus 50x1 plus 50x2. And now we move everything to the other side. So I have x1 double prime, 2, is equal to negative 150x1 plus positive 50x2. And then x2 double prime is negative positive 50x1 minus negative 50x2. And I'm going to divide the top by 2. That will give me x1 double prime is equal to negative 75x1 plus 25x2 divided by second one is x2 double prime, stays the same. There we go. Perfect. All right, cool. Now my big matrix M in this case is just 1 0 0 1. So nothing there, because we were lucky with masses, right? If the masses were 7 and 3, right, then we would have to find the inverse and multiply both sides. But because it was just simple like this, I mean, you can always divide with mass to the other side, and you will get, your standard. So you have your x vector that will have x1 double prime and x2 double prime. Then you have your matrix K, which is negative 75, 25, 50, and negative 50. And you have your vector x, x1 and x2. Woohoo! Right, so all of the good stuff that you are used to. Now, this happens to be A immediately because you have, right, it's A immediately. All right. So, and it's A because this is in identity matrix. That's why it's A. Otherwise, you would have to multiply by. But you will always, because guys, masses are always going to be some numbers. You can divide by those numbers, and you might get fractions in here, but you don't have to deal with the matrix inverse and matrix multiplication. You just deal with fractions with numbers, right? So it's like pick your poison, but when you do the matrix multiplication inverse, those will end up being the same fractions anyway. So such is life. All right, so I have my matrix A, which is negative 75, 25, 50, and negative 50. So I have the matrix. And then I am supposed to do the what we learned, right? We're going to hit this with the all of the calculations that we learned earlier for the matrices and obtain the solution, right, using the eigenvalue problem. So we are going to have our determinant of negative 75 minus lambda, 25, 50, negative 50 minus lambda. Oops. Determinant, right? Not the matrix, but determinant. So that is going to be negative 75 minus lambda times negative 50 minus lambda minus 50 times 25, that's what? 25 times 25 times 2, 625, 1,000, 250, right? No. My brain stopped working completely. I'm multiplying these two numbers. So that's 625 times 2. I can also multiply by 100 and divide by 2. So either of the two. That's going to be 1250. All right, whatever method. To get that, needs to be equal to 0. Why is M an identity matrix? Because you will always have masses, and the masses will always go here. And eventually, if those masses are whatever numbers, you will eventually divide by whatever those numbers are. And it will always work out to have coefficients of 1, and matrix, identity matrix has coefficients of 1. So you will always have coefficients of 1 there if you do this trick to divide each equation by its own mass, so you can get 1, so you are actually forcing identity matrix there, because that gives you A right away without messing with the inverse. Okay, so now we'll FOIL everything. What do I have? I have a lambda squared. Negative and negative is positive. So that's going to be plus. Add these two numbers, 125 lambda. And then, what do I have? Plus 75 times 50. I knew it that I shouldn't have multiplied, guys. Whatever. This is just going to be 50 times 25. Look at this trick. So this is going to be 50 times 75. 50 times 75 plus 50 times 25. That's the calculation. This is what I like about quick computing. I calculated too quickly. Lambda, And now when you pull out 50 as a common, oh, but that's a negative. This one is a negative. So pull out 50 as a common factor, and in parentheses you have 75 minus 25 lambda squared plus 120. I don't know why these things make me so happy, but plus 50 squared equals to 0. And oh, is this the... No, it's not. Whatever. We have to factor it. So what are the factors of 2500? Well, 1 and 2500. 2 and 1250. 3 doesn't work. 4 does work. 4 is not going to work here. No. 5. The difference is too small to make 125. So 5 doesn't work. How about 10? 10 and 250. That's not enough. 15, 25. 25 and 100. Yep, they add once. Great. So lambda plus 25, lambda plus 100 equals to 0. And I have lambda equals negative 25 and lambda equals negative 100. I have my two eigenvalues an hour later. So now we do the standard procedure to obtain eigenvector by plugging eigenvalue back into the matrix up there and figuring out eigenvector. So I have negative 75 minus 25, so lambda 1, lambda 2. Negative 75 minus 25, 25, 50, 25, 50, negative 50, and then minus and minus. Oh, this is a plus here. Make a plus 25 times the matrix AB needs to give us 0 matrix, or you can say 0 vector 2. So this is going to be negative 50, 25, positive 50, negative 25 times AB equals 0, 0. So if you are able to immediately see that your vector V, that's okay, right? Because you are supposed to multiply 50 by something and 25 by something and add them together to get 0, right? So my A, if my A is 1 and the B is 2, if I just pick 1 and 2, you can, right? If you are able to see it immediately without writing anything down, it's fine. If you not see it, then it's negative 50A plus 25B equals to 0. Now you pick A equals to 1, you get 25B equals 50, and B equals to 2, right? So if you see it, right, what two numbers you need to multiply into these so that give you 0? It was obvious that negative 50 plus 50 would be 0. You immediately have your eigenvector. So we have our eigenvector to be there. So we have our first eigenpair. Lambda 1 is equal to negative 25, and the V1 vector is given as 1, 2. That's our first eigenpair. Now we go with the second lambda. What was that? Negative 100, if I remember. So that's going to be 25, 25. And what did I say? I said, okay, the tablet is overheating and it's really getting laggy for me to write and scroll and everything. So now the commands are getting, in a way, 50 and negative. So I have a negative 100. When I plug in negative 100, I get 25, 25, and a negative 100, I get 50-50. Okay, 50-50. You see that the system is dependent. And for the dependent system, we can quickly just use 1 and negative 1 in this case, because that will give us the value for eigenvectors. So the second eigenpair is lambda 2 is negative 100 and v2 is 1 and negative 1. So that's our life. All right, so now the general solution over here. Oh my God, so come on. There it is. So the general solution from here will tell us what we are supposed to use as our values. So we can plug our values in and obtain the system which will contain all of the values that we wanted, so for x1 and x2 in this case, and then you can separate them. So a1, so these are your eigenvectors, and oh, I didn't talk about the omegas. I know, I shouldn't have skipped it. So maybe if I give as a formula over here, those of you interested in a derivation, right? If you're a math major, physics major, possibly electrical and mechanical as well, you know, it's worthwhile looking at the derivation of this. But my equation has an omega in here, and we need to know what the omega is. So omega squared is equal to negative lambda. That's what the omega squared is from here. And you can see that the complex values will pop out, right? Because when you square root both sides, you're getting negative square root. You're getting negative under the square root, which creates complex, which introduces trig. So where is this solution? Holy nightmare. It's been going forever. So, oh, by the way, this is the cheapest possible problem. 2 springs, 2 mass. That's it. You add 1 more spring, you add more mass to all of this. All right, so what do I have? My omega squared is equal to negative lambda. Now my lambda 1 is negative 25. So I'm getting that omega 1. So this is the formula. So I'm getting that omega 1 squared is positive 25, from where omega is 5. So that's something that it's important for you to know. And now you can write the x1 solution. Let me follow the same logic as k1 over and what is what? No, because this is a system. It's a second order system, and with second order system, you have we convert the second order system into the first order system. We use the substitution for the answer. So technically, if you are converting this into your second order system from chapter, I believe 2 or 3, whenever we did the R equation, I think it was 3, you are getting your x double prime plus kx, and then you have your r double prime plus that k is supposed to be omega. Oh, you mean that square root of k1 over, yeah, you can, yes. It follows, I mean, it has to be the same. It's the same concept. Now I understand the question. Yes. All right, fine. You're right. All right, so this is it. And now we have the lambda 2, which was negative 100, which means that omega 2 squared is going to be equal to positive 100 because the negative from the equation and the negative from this one gives you positive, from where we are getting that omega 2 is 10. Omega 2 is 10. So we now just write our solutions. So x1 solution of t, which is what we are looking for, is going to be some constant plus, right, another, so you can use just the C1 and oh no, we use the AI in the other one. So A1 cosine omega t plus B1 sine omega t, and x2 solution is A2 cosine 10t for the second one plus B2 sine 10t. Oh, this is a 5 sine 10t. There we go. Holy nightmare. It's a lot of mess. We're done. The problem is solved. We can make this way worse by adding more springs, by adding more masses. The number of masses is telling you how many equations you're going to have. So 2 masses, 2 equations, 3 masses, 3 equations, and so on. And you can attach different number of springs to it. And then you can introduce, I don't want to go into all of the mess that it's happening later with forcing terms and everything else. Resonance, you can add all of that mess as I mentioned before. You can add all of that mess in there and come up with systems that are even more annoying to solve. I don't want to solve it because we solved a lot of these things, but I would like to go and what are we going to use for V of, oh, thank you. Well, those are your A's and B's. Yes. So eigenpair 1 and 2. 1 and 2, and 1 and negative 1. That's the that's where you plug your vectors. Those are your A and B, A1, B1, A2, B2, and you can even compress this further using that phase shift. If you use the triangle method, you can condense this further. I mean, this problem can have more steps if you want to. If you want to show this as a single cosine using the phase shift alpha, you can condense this into a single one of the. It's just a lot of mess. I would just leave it there. let's take a look at setting up one with the 2 steps. So let's two masses. So one problem with 2 masses but 3 springs. Something from homework. So they give you, and then we're calling it a day. So we're going to have 2 masses. Mass 1, mass 2, and 3 springs, K1, 2, and 3. This is our displacement x1, this is our displacement x2, and if you remember, this spring is just x1, this spring is x2 minus x1, and this one is just going to be negative x2, right? Because it's in terms of the motion, right? Pick any problem, 1 through 7. They're all the same. I think they worked out the odd ones in the back, so you can check those solutions. If you're practicing these, I can pick. I guess I'll do one of the odd ones or even ones, whatever. Number 6. Let's say that's the worst, right? It's just all the same. Do I have any? Yeah, this one has different masses. Good. Mass 1 is equal to 1, mass 2 is equal to 2, K1 is equal to 2, K2 equals K3 equals 4. So 1, 2, 2, 4, 4. 1, 2, 2, 4, 4. Good. That's all we need, right? And as I said, I'm just going to set this one up. Solving is going to be exactly the same steps as above, it's just different numbers. My concern here is how to deal with M1 X1 double prime plus, and it has 2 springs. So we have K1 X1 and then minus, because it's opposing, K2 X2 minus X1 equals 0. Mass 2 x2 double prime plus K2 of x2 minus x1, and then it should be, well, minus K3 negative x2. That's going to give us a plus later. So I'm going to plug the numbers now. So 1, well, I don't need a 1, it's just x double prime 1 plus 2x1 minus K2 is 4. So 4x2 plus 4x1 equal to 0. Mass 2 is 2, so 2x2 double prime plus K2 is 4 x2 minus 4x1 plus K3 is 4x2 equal to 0. Add like terms and divide by 2, so it's going to be a lot of calculations here. X double prime 1 plus 6x1 minus 4x2. This is divided by 2, so it's just x2 double prime. And I have minus 4x1, come on, minus 4x1. Oh, but it's divided by 2, so it's 2. And then 4 plus 4x2, that's 8, divided by 2 is 4, so plus 4x2 equals to 0. Move the terms to the other side. So we have x1 double prime is equal to negative 6x1 plus 4x2. and then x2 double prime is equal to 2x1 minus 4x2. There it is. So finally you can come up with your matrix A as a negative 6, 4, 2, negative 4, from where you go into your eigenvalues, negative 6 minus lambda, 4, 2, negative 4 minus lambda. And I'm just going to do this. Just do it. It's your practice. The goal of this section is not to do this calculation. The goal is to learn how to convert the mechanical system with springs into equations. Solving these equations, that was sections 1 and 2 of chapter 5. So we're going to end over here. We have 2 or 3 sections left in chapter 5, so the next section is obviously on Friday. Let me just verify what we're doing here. So we're done with 5.4. Try a couple of examples to model this. Again, exam will see 2 by 2 case, obviously, so 2 masses. I don't know how complicated your courses will get once you transfer out, so knowing these with the 3 masses is also something that it's good. Maybe you want to even look into. Now, civil engineering people, if we should have some civil engineers here. Page 333 in the textbook will teach you about earthquake-induced vibrations of multi-story buildings. When you're designing a building, you need to make it earthquake-proof up to some degree. I'm just going to put it out there that the pyramids are standing for more than 5,000 years, right? So take a look at that engineering. Obviously, we don't have technology or knowledge to make any of those today, but yeah, it's interesting to read this section and see how the earthquakes impact, right, and vibrations induced. All right, so 5.5 is on Friday on multiple eigenvalue solutions. So that's something that we would have to look closely into. And then what else do we have? Matrix exponential, and that should be it, I think. They're non-homogeneous systems. 5.7 with a variation of parameters, right, and undetermined coefficients done on matrices, which is going to create a lot more mess than what we had in chapter 3. Anyway, it seems that we have 4 sections left. No, 3 sections left. 5.5, 5.6, 5.7. And we will be ready for exam, which means that the next week we will be ready for exam 2, and then we will have a little bit of time to cover. So we'll start Laplace transform next week, or no, we're going to do 2 lectures and a review. Yeah, so following week we're going to start, so following week will be devoted to Laplace transforms as far as we get in 1 week. Then the last week of instruction we are going to do power series, 2 sections, and we're going to do the course review so that you guys are ready for the final, and we'll talk about the final. If you are here for the first time after a long time, new syllabus is posted in Canvas files. It says new. Please read about new assignments. The project is no longer there. There is an essay now instead of it. So 2-page essay, no double spacing. If you double space, then 4 pages, which simply asks you what you have learned in this class, right? What kind of application have you learned So where could you use differential equations? And I am inviting you to think about the population and mechanical, electrical, civil, and obviously we haven't done much, unfortunately, with chemistry, but there are a lot of applications. Differential equations drive everything. I mean, 100% of physics and so on. It should literally be you just sit down very quickly and just write it up. I had to work out percents for the grade without the project, and going down 2 exams into one. That was a lot of percent. I really didn't want to make a final to be like 50-60% of the grade. So I made up that assignment to replace the project so it still can be calculated as the assessment, which is important for transfer, obviously, and for your grade to be valid. So let's see what you learned in the class. That will be due the day of the final exam. So make sure you are, I know some of you are going to sit and write it this weekend, which is the best, obviously, because you pretty much. Oh no, you haven't seen Laplace transforms yet, which is So wait until you see Laplace and then just write it out, and we'll leave the most powerful right. So Laplace transform is the engineer's favorite way of solving differential equations, and then power series at the end, which is the most powerful way of solving differential equations, which segues nicely into partial differential equations that some of you will be taking once you transfer out. All right, so that's it. Like and subscribe and hit the notification bell. Bye.